So we're doing the electromagnetic field in the Lorentz gauge. My throat is a bit funny this morning, so I'll maybe try to write more and talk less. So let's see. All right. I'll try and focus on what you really need to know. So, electromagnetic field. Lorentz gauge. So we use Fermi's form of the Lagrangian. Implies directly the wave equation in the Lorentz gauge. So the Lorentz gauge condition we'll have to impose afterwards. The point is, with this Lagrangian, it doesn't know anything about the Lorentz gauge. The question is this equivalent to Maxwell's equations? Well, only in the Lorentz gauge. So we're going to have to add the Lorentz gauge conditions somehow later in order to make sure that we're really doing electromagnetism. All right, so if you quantize this, this becomes an operator field equation, the usual thing. And as we said last time, well, this is like having four independent real Klein-Gordon fields. So the expansion field operator expansion looks like this. We have a sum over plane waves. So when I said four real Klein-Gordon fields, I meant four real massless Klein-Gordon fields. So here R is going from 0, 1, 2, 3, and omega is the magnitude K. And these, notice that these here, these polarization vectors are 4 vectors. They're not 3 vectors anymore, they're 4 vectors. And there are 4 of them. For each wave vector K, there are 4 polarization vectors, labeled by R as 0, 1, 2, 3. And we have the orthonormality and completeness relation. So these 4 vectors. So this is a 4-dimensional dot product. Same wave vector, different polarization indices. It's taken to be minus zeta R delta RS. Let's define here, let's write it down over here. Just introduce this, convenient to define a quantity zeta whose 0 component is minus 1, and zeta 1, zeta 2, zeta 3 are equal to plus 1. So in other words, if R and S are both 0, then this is plus 1, and this polarization vector is time-like. When r is 0, so for r is 0, this 4 vector is a time-like 4 vector. When r is 1, 2, or 3, this is a space-like 4 vector. And there is also, there's a completeness relation, which I'm going to explain following epsilon mu kr, epsilon mu k, whoops. So these are two polarization vectors with the same polarization index, multiplied by this quantity, summing over r. This is equal to minus the metric tensor. Should have written that down properly. Okay, now you may wonder what on earth this is. So this is where we were last time. Let me explain. Just explain. This thing here just says that it just says that the epsilons form a four-dimensional basis. You've taken the epsilons to obey this relation in order for them to consistently form a basis with this metric tensor. You have to obey this relation. Let me explain this if you've maybe never seen anything like this before. It's actually quite straightforward. By the way, last time at the very end, I think I wrote something wrong. Let's think of the two abstract. Let me just explain what this explain this relation in case it looks odd to you. Imagine I have abstract 4 vectors u, v. Their components in an arbitrary basis. You might write as u mu, v mu. And you have an inner product u dot v is g mu mu u mu v mu. Okay, that much you know. Now what I can write, we can write u v in the basis epsilon kr. Okay, here I've got 4 unit vectors. Okay, these are 4 unit vectors in space-time. So I could write u is ur epsilon kr, v is vr epsilon kr. So there's a sum over r. For some reason, at the end of the last lecture, I was sort of in a bit of a hurry. I think I wrote this. This is nonsense. I mean, here's an abstract 4 vector. This will be the inner this is the inner product of u with epsilon kr. Okay, that's not. I meant to write this, but anyway, if you've written that in your notes, just go back and erase that. Okay, so here's what I'm thinking. That u. So this is just like saying, look, I can write. You know, if you're used to three-dimensional vector analysis, I can write an abstract 3 vector as a linear combination of unit vectors with components. This is the same thing. I can write abstract 4 vector as a linear combination of these unit 4 vectors with these components. So in other words, these are the URs, these are the components of the 4 vectors in this basis formed by these 4 polarization vectors. So in order for this to be consistent, let's just check, hang on, what is the inner product? The inner product of U and V. Let's just write it out in terms of these components. So these are components in arbitrary basis. Let's write it, sorry, okay, something else I should say. If this is true, then U mu is going to be what? It's going to be the component of U in an arbitrary basis is going to be U r epsilon mu kr. And V mu is VR epsilon mu kr. You don't really need to go into all this. I mean, the main thing is that you know that this completeness relation is applied. I'd just like to go through and explain to you what this is in case you've not seen something like this before. Now again, this would just be like saying, well, in an arbitrary basis, maybe if I was looking at here are the components of U in the ijk basis. If I wanted the components of U in some other basis, let's say the component Ui, what would it be? It would be U1, I, U2, J, I'd have to work out the components of ijk in this basis. Okay, I'm not writing anything, nothing really difficult. Anyway, so there you go. So now we're in a position where we can say, hang on, let's look at the inner product of U mu U nu. Okay. So let's write the components in arbitrary basis in terms of the components in this basis of polarization vectors. So we have U r epsilon mu kr. Let's write here r. Here we've got r's. Let's put r primes here so we don't get them muddled up. So we've got V r prime epsilon mu kr prime. And now let's put in let's maybe go up here. I'm going to make this a bit wonky. Let's go up here. Let's put in this expression here. This funny looking expression. You're thinking, what on earth is this thing? Alright, let's put this expression in. So minus, let's write it as a sum over S. Let's do it in index S so we don't get muddled up with the R and the R primed. And in fact, is R, okay, let me put the summation sign in. I'll put the summation sign in, epsilon K. So I'm lowering the indices mu and nu. So I've got epsilon K S mu, sorry about all the indices, K S mu. Alright, this is just the expression for G mu nu. From there I've just lowered the indices mu and nu. U R epsilon mu kr, VR prime epsilon mu kr prime. And of course here I've got a sum over S I've written explicitly, but there are sums over mu's and nu's, and there are sums over R and R primed. Alright, let's just rearrange this a little bit. Minus the sum over S, zeta S, epsilon K, S mu, epsilon mu, K R, epsilon K, S nu, epsilon mu, K R prime, U R V R prime. Alright, so now what do we have here? Minus the sum over S, zeta S, what is this thing here? This is just the inner product of epsilon k. This is just epsilon ks dotted with, okay, that thing, just the inner product of epsilon ks with epsilon kr, which we have from this relation here. So in other words, we can write this as minus zeta r delta rs, and similarly, this here is the inner product of epsilon s nu with epsilon kr prime. So that's minus zeta r prime delta r prime s u r prime. Of course, here there's a sum over the r and r primes. So what is this thing? So summing over the r and r prime both have to equal s because of the Kronecker delta. So you get minus sum over s zeta s us ds. Okay, and finally, hey presto, because of these values that we've defined, what is this thing? This is just u0 v0 minus u1 v1 minus u2 v2 minus u3 v3, which is what it's supposed to be. Remember, we started out working out the inner product here. Okay, so it's just a consistency relation. If you're saying that these four quantities are four vectors that form a basis, and they are normalized like this, they are orthonormal like this, then in order to be consistent with the metric structure, they have to obey this completeness relation. So this is completeness, and this is orthonormality. Okay, anyway, so there you go. So it has to be. All right, so we have these polarization vectors form a basis in four-dimensional space-time. And what we're doing, so if you think about it, of course it has to be, what is this expansion saying? It's saying, well, at each point, imagine one point in space-time. Imagine you fix x, some value of t in some position in space. And these are just numbers. Okay, and if I haven't, let's say before I've quantized, well, the level, if these are not operators yet. Okay, let me write it like this. Let's say I'm looking at a classical field, and I'm expanding it like this at a given point in space-time. I have a four vector, and we're saying that, well, I can write the four. So this is a function on space-time. At a given point in space-time, there's one four vector, and this is saying, well, that four vector can be written as a linear combination of these four unit four vectors. Those simple thing. And then, of course, this is true at each point in space-time, and then, of course, we promote all this to an operator, and there's our expansion. Okay, so good, there we go. So that's something. So the expansion here, this is important, of course, the orthonormality and completeness relations. And let me give an example. So, example of, so this four-dimensional basis. As usual with a four-dimensional basis, there's a certain arbitrariness, but here's a choice that you can use if you like. So notice it's always true. It's always true. Epsilon cos K0 is time-like. Okay, when R is 0. The polarization vector is time-like, and epsilon kr, r is 1, 2, 3, are space-like. Okay, that's clear from these orthonormality relations. So let's look at an example. It's sometimes useful to have a particular example you can take in a certain frame, in a given reference frame. So let's say normally you're trying to make this thing explicitly manifestly Lorentz covariant. But if you say working in a given frame, you might say, okay, in a given frame, what's an example of these vectors? I could choose the following time-like vector, just be 1, 0, 0, 0. So it's just a unit vector along the time axis. And then I can take epsilon kr. So for r is 1, 2, 3. So here is r is 0, r is 1, 2, 3. I can take the 4 vector to have 0 time component and to be purely spatial. But these are now spatial, these are 3 vectors. And we can take epsilon k3 to be a unit vector along the direction of the wave vector, and we can take epsilon k1, epsilon k2 are your usual polarization vectors that are orthogonal to polarization. Of course, they're unit vectors and orthogonal to k. So remember when we did the quantization in the Coulomb gauge, we had just these 2 polarization vectors. They're unit vectors orthogonal to k. So k dot epsilon k1 is k dot epsilon k2 is 0. Here we've got 2 extra polarization vectors. Now these are referred to as transverse polarization. This thing here is called longitudinal polarization. And here we have scalar or time-like polarization. Now, the only physical polarization states are these ones. These are the 2. These are unphysical. We still have to impose the Lorentz gauge condition. So we have too many degrees of freedom. Too many degrees of freedom in this theory. This is electromagnetism plus other stuff that shouldn't be there. So we'll see how that works. But for the moment, anyway, here are examples of these polarization vectors. I can choose one to be purely time-like and the others purely spatial. And you see that in the spatial components, you've got the polarization vectors that you're used to, plus a longitudinal one in the direction of k. And then, of course, here there's a purely time-like polarization vector. Okay, so sometimes when you're doing a calculation in a given frame, it can be useful to say, okay, let's pick some polarization vectors, and often these are usually useful to choose them in this form. Okay, let's move on. So we've got our Lagrangian density. We have our expansion of the field operator. We have to figure out what the observables look like. So, all right, you are advanced quantum field theorists. I can whiz through this, and you can check through the details if you, as you wish. So, let's look at the conjugate momenta. Conjugate momenta. So let's look at the canonical momentum density that is conjugate to a mu. Okay, so by definition, it's a partial derivative of the Lagrangian density with respect to a mu dot. This comes out to be equal to minus a dot mu with the index lowered, or you could write this as minus g mu nu a dot mu with the index raised. You might want to check that. Simple thing, there's a Lagrangian density, easy enough. You can check that. So let's see, hang on, I missed something out. All right, so now, canonical commutation relations. You know the general form. I have a field, I have its canonical momentum density. The commutator is equal to I times the three-dimensional Dirac delta function. So here it is. Here's my canonical momentum density. The canonical commutation relations take the form. So here is a mu x t. So writing pi in terms of a dot, taking into account this factor, the metric, you get the following. So we have an a dot mu x prime t is equal to minus I g mu nu delta 3 x minus x prime. So here I recommend that you check this as homework. So if I just write down, hang on, I've got my canonical momentum density conjugate to a mu. So write the relation in the usual form. So you're going to have something like a hat mu, and you have pi hat mu is equal to I delta mu nu delta 3. This would be the usual relation. I've got the field operator, its canonical momentum density, and this would be the usual relation. Okay, that they commute if the indices are different, if the indices are the same. So then this is 1, this is just a Kronecker delta. This is the usual relation. If you insert this value here and you multiply both sides by g mu nu, fiddle a little bit, you should get this. Okay, you should get this. All right, so now if you look at this, this should remind you of the Klein-Gordon field, where of course pi was just phi dot, and we had canonical commutation relations schematically looking like this. We had a commutator of phi and phi dot equal to I times the three-dimensional Dirac delta function. Here we've got the same thing, there are 4 of them, except, hang on, it's not quite the same thing. Remember, g mu nu, we're taking it to be 1 minus 1 minus 1 minus 1. Write non-zero components is plus 1, minus 1, minus 1, minus 1. Diagonal components. Diagonal components of g mu nu are plus 1, minus, minus, minus. So when mu and nu are spatial indices, this is plus I. There's a plus I, so it looks just like this. When mu and nu are equal to 0, the time-like indices, this is -1, we get a minus sign. So something funny happens. So in other words, we've got a mu is 0, we have a minus sign. Mu is 0, there's a minus sign in the canonical commutation relation. So it's like having this, it's like having a Klein-Gordon field, but with a minus sign here. Something funny happens. And we're going to see that something very funny happens to the time-like components. So, all right, so let's just move onwards. Let's see, maybe I will. Okay. All right, next something, okay, let's just do this now. Let's just, Feynman propagator is something important that we'll need later. So the Feynman propagator here is defined to be, so this is the Feynman propagator for the electromagnetic field written in the covariant Lorentz gauge. So Feynman propagator, what the definition? So it's the expectation value of the time-ordered product of A mu x primed, and what you find is, notice I have 4 massless Klein-Gordon fields. Essentially, this is like having 4 massless Klein-Gordon fields, but with a factor if you look at this, say, well, it's just like having 4 massless Klein-Gordon fields, except there's this factor G mu nu. So if you go through the calculation to find the Feynman propagator, what you find is that, well, the Feynman propagator is just equal to what he needs to take the limit as the mass goes to 0 of minus G mu nu times, this was the Feynman propagator for the Klein-Gordon field, which we worked out before. So you get the same thing, except you want to put the mass as 0, and there's this funny factor minus G mu nu in front. So in other words, what you get is, writing it in terms of the integral representation, is we have an integral, and again with bosonic fields you tend to write k instead of p. It's just a convention, e to the minus I k dot x divided by k squared plus I epsilon. So in momentum space, so this is what we're really going to need to know. This factor is going to come up all over when you're doing calculations with scattering electrons, so on, processes involving photons. The Feynman photon propagator is often called, in momentum space, takes the following form: df mu nu of k is equal to minus G mu nu over k squared plus I epsilon. Epsilon is positive and going to 0. There we go. That will be important. That's important to know. Find the photon propagator in momentum space. Minus G mu nu over k squared plus I epsilon. Okay, let's move onwards and upwards. The usual business is, what do we do? As I've said now a number of times, you're advanced field theorists. I said, enough times, you might start to believe it. So, what you do, you know how the game works now, is you insert the field expansion A hat nu, which is a sum over KR. You just write it schematically, A hat KR plus A hat dagger KR. Okay, but there's a factor here, I've got the x to the plane wave, blah blah. I insert the field expansion into, of course here I wrote down the canonical commutation relations. There is of course the etc., which just says that, well, the A's commute with themselves, the A dots commute with themselves, so their commutator equals 0. We don't bother to write them down, we just call it etc. Anyway, the non-vanishing commutation relation is between A and A dot. Anyway, you've got this field expansion for A, so you can find the field expansion for A dot. Take the time derivative, insert into here, and you can find what you do. So you can write the commutation relation in terms of the A's and the A daggers. So you can find, in other words, what do you find? You insert the field expansion into the canonical commutation relation for A and A dot, and you find, and you can check this if you like, you find the following. You find A hat commutator of AKR with A dagger KR is equal to, now you might think what you normally expect is that it would be delta RS delta K K primed. Okay, that's what you know. Hang on, sorry, AKR. What am I doing? What's the matter with me? Sorry. A hat KR, A hat dagger, K prime S. Okay, it's just the normal commutator between AKR and A dagger K prime S. So normally you would expect, well, different wave vectors. I have a Kronecker delta, different polarization indices, Kronecker delta. That's what you would expect. If all these indices are equal, then this will be 1, and I'll have the usual commutation relation for the oscillator raising lowering operators. Sadly, there is a complication that damn zeta thing appears here. Now remember zeta 0. Zeta 0 is minus 1. Zeta 1, Zeta 2, Zeta 3 are plus 1. Now remember I said something funny happens. So you see that when R is 1, 2, or 3, I get the usual commutator for A and A dagger. When R is 0, there's a minus sign. So in other words, R is 0, let's write down for one with wave vector AK0, A hat dagger, let's put K prime equal to K. And R and S, let's put R and S, both equal to 0. So we have commutator of A and A dagger is minus 1 for time-like photons. The commutator of A and A dagger is minus 1. Trouble. Let's look at this. So remember I mentioned to you, time-like photons and the longitudinal photons are actually unphysical. For the time-like photons, something totally bizarre happens, and this will shock you, so be prepared. Okay. Let's look at a state let's look at the state with one photon, with polarization index R. What is that equal to? It's equal to A dagger KR acting on the vacuum. Let's look at the inner product of this one photon state with itself. It should be 1. It should be 1. So what is this? It's equal to 0, taking the adjoint of this relay, so I can write 1 KR is equal to 0 A hat KR. Okay, so this is just A hat KR, A hat dagger KR, 0. And what is this equal to? Well, from this commutation relation, A hat KR, A hat dagger KR, putting S equal to R, and K prime equal to K, this is equal to, so minus K prime equal to K, S is equal to R, so these are 1, I just get zeta R. So this is minus 1 when R is 0. Anyway, I can write this as 0, I can write zeta R plus A hat dagger KR, A hat KR, acting on the vacuum. Okay, I've just written this equal to zeta plus putting this on the other side. This term, the annihilation operator acts on the vacuum, it gives me 0. So this is just equal to zeta R. This is just a number. If the vacuum state is normalized, it's zeta R. So the inner product of this photon state with itself is equal to zeta R, which is equal to minus 1 for R is 0, and plus 1 for R is 1, 2, 3. Now this is terrible, because in a Hilbert space, the norm, any physical vector, any physical vector, the norm, any physical vector psi, norm is positive. If it's a 0 vector, then 0 is not a physical vector. The norm has to be positive. The norm, the magnitude of a vector by definition is positive. It cannot be negative. So what you have, this is unphysical. And in fact, as I mentioned before, these are called ghost states. Ghost states, these states with negative norm, they're often called ghost states. They're not physical states. So what on earth do we do here? Okay, so there are actually some slightly different ways of handling this. The most common method, I think, is often is often called the Gupta-Bloiler approach. Is what you do is you say, let's just proceed ignoring this. And then when we add the Lorentz gauge condition, we'll see that something useful happens. Okay, we haven't yet imposed the Lorentz gauge condition. Let's just, so formally, ignoring the fact that we have this total BS, you call them BS photons, but that's not a, it's not a term you'll find in the literature. They're called ghost photons. Anyway, formally, if I say, well, let's take my expression for the Hamiltonian that I derived from the Lagrangian density. It's an integral over space of the a dot squareds and blah, blah, blah. You can look this up and work out, find the expressions of the Hamiltonian of the electromagnetic field. Insert the field expansion, the usual thing, you've done this over and over now, to find the expression for the Hamiltonian in terms of the A's and the A daggers. What you find is the following. Sum over KR, omega, there's this damn zeta factor there. A dagger, and KR. Okay, so it's what you expect to find. It's just what you expect, except for this zeta factor. Remember, of course, omega is mod K. Now, you might think, so what on earth do we do here? There's a minus sign. When R is 0, there's a minus. What are we going to do here? So what Dr. Broiler so this is just by straightforward, you take the canonical expression for the Hamiltonian density, you integrate it over space, write the field operators in terms of the A's and A daggers, this pops out. Now what Compton Broiler do is say, let's continue to define the number operator. Let's define the number operator to be equal, instead of it being equal to A dagger A, we're going to define it to be zeta R, A hat dagger, KR, A hat KR. Okay. But there is this problem. Well, the time-like photons have negative norm states. So what does this even mean? You can just, you formally are writing down these equations, but there's something, there are unphysical components in these equations. So now here is where all of this problem at the end of the day goes away, because let us now impose the Lorentz gauge condition. Okay, as I mentioned, if I try to impose it at the level of the operator field, this conflicts with the canonical commutation relations. You take the canonical commutation relations and you take the derivative of each side and you assume that this derivative of the operator vanishes, you get a contradiction, so you can't do that. But what you can do is you can impose the following condition. You can say that physical states psi must satisfy that the expectation value of d mu a mu is equal to 0. Okay, we're going to impose that as a condition. What is happening here is we have states that are unphysical. So the state 1k0 equals a hat k0 is unphysical. Okay, it has negative norm. What we really have, you ended up with a Hilbert space. You don't have you have a physical space, which is a Hilbert space, where all the states have positive norm. But then there are extra vectors, appearing in this formalism that have negative norm. It's not even the proper Hilbert space. So what you want to do is you say, well, the physical states are restricted. So you've got this large vector space that includes states with negative norm. But what you say is that physical states are restricted to a subspace. To a subspace. So there's a subspace of the vector space that is defined by states that satisfy this condition. So what we're saying is, well, you will recover the Lorentz gauge condition at the level of expectation values, not at the level of operators, but at the level of expectation values. Now remember that for the quantum field theory to be consistent, it has to give you the correct classical limit. Okay, the first test of any quantum theory is, well, do I recover the classical theory and the classical limit? So to recover the correct classical limit, you don't have to have the Lorentz gauge at the level of operators. It's enough to have the Lorentz gauge at the level of expectation values. So in the classical limit, the theory will satisfy the Lorentz gauge. Now, what happens? I'm not going to go into this because it's all a bit fiddly and not very illuminating. But if you're interested, as homework, check and look in the book. The book has a page or two about this. That if you look at this condition, this implies a constraint on the possible combinations if you look at a general state, it will contain time-like photons, longitudinal photons, transverse photons, and what this condition does, it says, well, for a state to be physical, for a state to satisfy this condition, this state will contain various numbers of transverse photons which are physical. It will also have longitudinal and time-like photons that are unphysical. This constraint implies a constraint on the possible combinations of longitudinal and scalar photons. The longitudinal and scalar photons at the present have to appear in certain combinations. And if you're interested, you can look this up in the book. But the implication of this, it's the implication that we're interested in, is that only transverse photons are, so with index R is 1 and 2, only the transverse photons actually contribute to the physical observables. So as an example, that they show you in the book, which you can go through if you're interested in seeing exactly how this works, is if you look at the expectation value, if you consider a state psi such that the expectation value of this expression is 0, then look at the expectation value of the Hamiltonian operator. And the Hamiltonian operator is given by this, and I've got R is summed over 0, 1, 2, and 3. What you find is that it reduces to the following. It is equal to the expectation value of, I have a sum over K, and the sum from R is 1 to 2 of omega A hat dagger KR A hat KR. In other words, the contribution, what you find is that the other terms involving R is 0 and R is 3, they actually cancel out. Contributions from R is 0 and R equals 3, they cancel. Because as I said, imposing this relation here means there's a certain constraint on the possible combinations of the photons that are present with R is 3 and R is 0. And what you find when you then look at any quantity that you're interested in, you look at the expectation value, and the contributions from R is 0 and 3 end up cancelling. So, the moral of the story, let's write down the moral of the story, because the annoying thing about this covariant form is that the formalism becomes very complicated and clunky. But at the end of the day, the result is quite simple. So here is what you really need to know, is that because of this, let me write you this conclusion. So the unphysical photons with R is 0 and 3, they appear in the general formalism. So, I mean by the general formalism, in the field expansion, etc., particularly in the field expansion, they appear in there in the field expansion. And they appear there in order to make the theory manifestly Lorentz covariant. You may have noticed, for instance, the expression for the Feynman propagator in momentum space. There's a minus g mu over k squared. It's a Lorentz covariant quantity. There's the metric tensor there. It's a Lorentz covariant. Which is useful. It can be useful to say, well, when we come down to write down the Feynman rules, the expressions are Lorentz covariant. So it's useful to have done this. But there is this extra stuff appearing in the formalism that's actually unphysical. So there's an upside and there's a downside. The upside is manifestly Lorentz covariant. The downside, I've got these extra unphysical photons in there. But they can be, here's the nice part, they can be ignored in the physical initial and final states. So they do not contribute to the physical observables. So if you have a physical initial state, you say, imagine I've got, I don't know, an electron and a positron and two photons coming in, and they're going to collide and scatter off each other. You could say, mathematically speaking, well, there could be some combination of scalar and longitudinal photons in there, but they won't contribute to anything that you measure. So you may as well just not have them there. It doesn't make any difference. So what will happen in this theory, the way the theory is used, is that initial and final states physical initial and final states. So in effect, let me write this, so in effect, physical initial and final states contain transverse photons. R is 1 and 2 only. So, so what's going to happen? So next week we're going to move on to the interaction between the. It's getting really exciting next week. Looking at the interaction between the Dirac field and the electromagnetic field. And let's imagine okay, so we've got the Dirac field. Dirac. There's an interaction Hamiltonian that we'll write down. So here is the Dirac field. Hang on. Let me write this. Spread it out a bit. So we have two fields. We've discussed the free Dirac field, we've discussed the free electromagnetic field. Now they're going to be interacting with an interaction, a specific interaction Hamiltonian that we'll write down. The Dirac field, remember the free Dirac field, you have all of these different modes with different momenta, P, different momenta, and polarization, sorry, and spin indices. Each mode is labeled by momentum and the spin. And each mode can be either unoccupied or occupied. Remember, you can't have more than one excitation in the same mode. And the Dirac field, because it's complex or non-emission, there are two types of modes. There are the electron modes, and then there are the positron modes. So here you have another set of modes, also labeled by momenta and spins, which can be occupied or unoccupied, and these correspond to positrons, which is excitations with equal and opposite charge. For the electromagnetic field, what we have is we have modes labeled by wave vectors k and polarization indices r, where physical initial and final states have r equals 1 and 2 only. Okay? For a mode with wave vector k and polarization r, you can have, of course, now the excitation can be arbitrarily high. I could have 2 excitations or more, n excitations in the same mode. Here maybe there's just 1 or none. But the physical initial and final states of r is 1 and 2 only. R equals 0 and 3 appear in the field expansion. So the field expansion that we wrote down earlier is correct. Remember, you've got a sum over 4 polarization vectors. You've got A at mu is the sum over KR, epsilon mu KR, blah, 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 blah. Here R goes from 0, 1, 2, 3. Okay? In the field expansion, in order to make this thing look Lorentz covariant, there are indeed 4 independent polarization vectors, including R is 0 and R is 3. They appear in the field operators. But the actual initial and final physical states have R as 1 and 2 only. Okay? So really, the electromagnetic field, physically, that we get here from this Lorentz covariant is just exactly the same. Remember what we did before when we quantized it in the Coulomb gauge? We had a set of modes like this with these labels where R could be equal to 1 or 2. Okay, there are transverse polarizations. The actual set of physical states is exactly the same. Exactly the same. Okay, there's no difference. So when you're thinking about, okay, what are the possible states of photons? This is what it looks like. It's exactly the same as what we did in the Coulomb gauge. The nice thing about the Coulomb gauge is that it gives you directly the physical states of the photons. This Lorentz covariant gauge, you've got this physical photon state plus this other stuff that appears and that isn't really physical. Okay, so now the point is, so that's what it looks like, and what we're going to be doing is things like the following. Imagine something like, say, Compton scattering. Say Compton scattering, where I have a photon coming in, photon, I have an electron, and they scatter. So here you would have a certain incident momentum. What you say is the initial state. There's a certain incident momentum and polarization. Here the electron has some initial momentum and spin. They scatter off each other. There is a final momentum and polarization, and there is a final momentum and spin. So what is the initial state? The initial state is, for this case, we have A hat dagger KR, C hat dagger PS acting on the vacuum. Okay, we've taken the vacuum state and we're saying that one of the electron modes is excited. So we're actually up here, and this one there's nothing. Okay, one of the electron modes, PS, is excited. There's one electron with momentum P and spin S. Okay, so a creation operator is acted on the vacuum. There's one photon present with wave vector K and polarization R. Remember, R is only 1 or 2. Okay, so we're saying that one of these, so this is down here, ground state, and here we're up here. This mode here is excited. So you will often write this as simply different ways of writing it, PS, or you might want to write it as 1KR, 1PS. Say, look, there's one excitation mode KR, one excitation mode PS. That's our initial state. That's our initial state here. The final state. The final state that we're looking at is, of course, just the same thing, but with K prime, R prime. E prime, S prime acting on the vacuum. In other words, this is K prime, R prime, or if you like, 1. And what we want to do is we want to calculate here is the task that we have for the remaining lectures, is we're going to calculate the probability for the transition. So let's call this initial state I, and the final state, let's call it F. So what is the probability for the transition? The initial state to go to a final state. So in other words, I say, well, if I have this initial state, and I let the fields interact, or I let the photon and the electron interact through a certain interaction Hamiltonian that we're going to study, what is the probability that later on I have a state where the photon has a different momentum and the electron has a different momentum? Remember, what's going on from the point of view of quantum field theory is during this transition, we discussed this before, but during this transition, what is going to happen is that the initial state, which looks like this, and the initial state looks like this. These modes are excited, these modes are not excited. The final state looks like this. The PS mode is not excited, the KR mode is not excited, the P prime to S prime mode is excited, and the K prime R prime mode is excited. So over time, this initial state evolves into this final state, where initially these modes are excited, they become unexcited. These modes that were not excited now become excited. So there's a transfer. Some modes initially excited, these are not excited. Later on, it's the other way around. That is the field theory description. We know when we say, oh, a photon and an electron have scattered. These are the initial momenta, these are the final momenta. And classically, you think of these two particles moving, and they hit each other, and they do this. From the point of view of quantum field theory, what's happening is this. These field modes are initially excited, these are not. Later on, these becomes de-excited, these becomes excited. Okay? And so what we have to do is calculate the probability for this transition. Now, it's similar to, remember what we've done already in the past, when we had an atom, for instance, it was excited in the vacuum, and then it emitted a photon, so the state of the electromagnetic field made a transition where there are no photons present to a state where one mode is excited. It's going to be a similar thing, except instead of an atom with the electromagnetic field, it's the Dirac field and the electromagnetic field. Okay, so think of what we did before. Think of this as being a bit like your atom. This is a bit like your atom. And here's the electromagnetic field. Instead of the atom interacting with the electromagnetic field, we've got the Dirac field interacting with the electromagnetic field. Okay, that's the subject for next week. All these wonderful things coming your way. If anyone has it, so we've finished with the theory of free fields. We're moving on to interacting fields and transition processes. So please make sure you understand everything so far. If you have any issues, please email me for an office hour, and we can go through any problems that you may have. All right, so see you on Tuesday.